Just about to start. Okay. Are we live? This is good. All right, cool. So welcome to AI at the Farthest Edge. Kind of a quick panel discussion on this kind of unique area of Edge AI. I'm Pete Bernard, CEO of the Edge AI Foundation. If you're not familiar with the Edge AI Foundation, we're the world's largest community of developers and technology providers for Edge AI. And we have a number of partners here today. We're going to talk about this topic about the farthest edge. You know, what is that? What are some of the unique properties? What's happening in this space? It's really, for me, I feel like it's kind of one of the most interesting frontiers for Edge AI because of the kind of unique, kind of low property, new architecture, things that are happening in the space. So why don't we do some introductions and we'll kind of walk through, give your 1 minute spiel.
Thanks, Pete. My name is Sumeet. I'm one of the co-founders of Innatera. We're a Dutch semiconductor company down the street from here, and we build microprocessors which work just like your brain. We bring intelligence directly to sensors, and we allow sensor data to be processed about 10,000 times more efficiently than conventional microcontrollers available in the market today. Our chips have just entered production, and hopefully soon you'll be able to buy them in a device that you buy off the shelf.
Hi all, I'm Brian Smith, Head of Sales and Partnerships and Business Development at Atym. We're a software company that's making it possible to take containers like Docker and run them on microcontrollers, so lighter weight containers. So in this application, what's interesting is in more capable systems, you deploy your AI models in software containers and run them on systems. But you don't have that ability today with microcontrollers because you have this monolithic firmware type base. So we make that now possible, where you can take containerized AI models and run them down on microcontroller type devices.
Hello, I'm Mark Goranson, CEO of EMASS, a NanoView company. And basically what we are is a RISC-based processor that sits exactly on the edge, meaning that we take multi-sensory input, whether it's temperature, humidity, pressure, light, movement, image classification, wake words, whatever it is. We take that data, we have a AI processor sitting right there, and we process this information right on a single chip. So we're down into the microwatt range where we're listening and sensing all the different sensors. And when we're under load, we're down into just milliwatt range. Latency is also very important as we're in mission critical applications such as automating drone flight times, looking at how we can optimize drones. And so we're taking that data real time as fast as we can, modifying it, and we're actually improving drone flight times by anywhere between 60 to 80%. So things that safety critical, things that need immediate detection and immediate AI, that's exactly where we play. So that's where we have defined the extreme edge AI.
All right, sounds good. So yes, all three companies representing the farthest edge in some form. I think you mentioned 10,000 times more power efficient than an MCU for AI, which is impressive. So first question, not really a taxonomy question, but you know, we get the question about what is edge AI, but when we talk about the farthest edge, like what are some of the unique properties? And you touched upon some of the things that your companies are doing that really defines this space. You know, a lot of people think of AI as ChatGPT, which it isn't. But what are some of the unique challenges of running AI workloads, or I guess in Atym's case, orchestrating workloads in this highly constrained environment?
So I think today there's been a lot of attention towards large language models being applied to processing data. And one of the unspoken challenges of AI is actually how much power is being consumed to run these models. And we've seen in a number of use cases, for instance, take a video doorbell where you're trying to figure out who's in front of your house. Traditional AI approaches tend to draw so much power to do this sort of analysis that device batteries in most doorbells today discharge in a matter of a couple of weeks. And if you look at the rated battery life on these devices, they're supposed to last you for about 6 months. And that's really where the crux of the problem sits. Conventional AI tends to be very inefficient. And where new approaches to edge AI are really changing the game is that they're making it possible to do always-on processing of sensor data. Always-on means you're ingesting data from the sensor as it's produced, you're frequently operating in the same power domain, and you're actually doing it with such little energy that these batteries can actually last for years at a time. So think of a doorbell that you don't have to recharge for a couple of years. This is essentially what we're able to enable with our processors, for instance. Another problem that you're able to overcome with very good edge AI is you eliminate the need to transmit data from the sensor towards the cloud. And the communication part is a critically underrepresented aspect of the problem. You don't think of how much energy it costs when you do a Google search. When you do a voice search, you're not really thinking about how much energy is being consumed, but actually it's a fair bit. And with very efficient AI at the edge, you're able to cut all of that communication down, protect privacy by processing data directly at the edge, do it fast, and do it in an energy efficient manner.
So I'll talk about this from more of a software kind of development perspective. When we think about bringing AI to the very farthest edge, what we're talking about are devices that typically have been, quote, dumb, right? Or have been very fixed in kind of what they do. So we're talking about kind of monolithic firmware, right? Software development that's kind of been done the same way for many years. But now we have this new AI model that we need to now run on these types of devices. And so there's a completely different approach that you need to kind of think about. One way is brute force today. Machine learning model or AI model is developed, and the way it gets into that monolithic firmware is brute force. You kind of take that code that comes out of all the ML tools, right? Ultimately is a C library. And so you have machine learning engineers that ultimately have to produce a C library that they typically don't know how to integrate with because they're not C development, they're not embedded development engineers, right? They know AI models. And so that's one of the challenges that we're seeing that is making it a little bit more challenging when you think about bringing that machine learning type concept to the furthest edge. That's a solution that we're helping to solve. But that's one of the unique things, not only in the power consumption and addressing that, but also in the software development that needs to be thought about differently.
Yeah, for us, we actually looked at it from a different direction. We looked at it from the sensor level, the data that has to come from the sensor level. How can we put the intelligence as fast as we can to the sensor level? And so we re-engineered the concept of having to go to a processor. We actually take the AI model, put it right next to the sensor, so we can take and sample the sensor data immediately, run it through an AI model, and only use it when we absolutely have to. So we actually measure latency in milliseconds, and we're down into the microjoules of energy per inference. So our whole idea is to make coin cell batteries where they can literally last for months or years on certain applications while we continue to sense, analyze, and use this data programming, and only do it to the cloud when we absolutely have to. Right now, all your data is going to the cloud, and then it gets processed, and then it gets shipped back. So our model is to take that data using as few energy as possible, as fast as we humanly can do it, and then be able to do that. So we're, like we say, we're at the extreme edge where this AI is sitting exactly right next to the sensor, doing all the polling, doing all the inference, and then after we need to, we process it on the processor, and we only use the cloud when we absolutely have to, because what we look at it is there's no cloud, no power, no anything. This has to be very small form factor with, very long battery life, and that's exactly where we operate.
Yeah, the phrase I hear is, you want to bring your AI to the data, not send your data to the AI. So the idea of sending data to the cloud or somewhere else to have AI processing is incredibly inefficient. And so you all three of you mentioned some interesting kind of challenges. What do you see as like, and this is kind of like your favorite deployment part of the talk, some of the scenarios that are uniquely enabled through kind of this farthest edge technology that just couldn't be done without this type of tech? Like, what are some of the, you mentioned about drone flight time extension, and obviously batteries that last quote unquote forever. But what are some of the deployments that you've seen out there or are working on, if you can share, that are uniquely enabled through this kind of farthest edge technology?
So I can talk about one of the recent products that was announced integrating one of our chips inside of it. Imagine you're in Las Vegas. You're at the Venetian, which is a 1,000-room casino hotel, and there's a fire emergency, and you've got to evacuate the building. When fire services arrive, how do you tell them which rooms are occupied and which rooms are empty? Do you actually go and check each one of those rooms? You physically can't do that. So what one of our customers developed is an intelligent smoke detector. It's a little device that runs on a battery that you replace once every 5 years. And they use that detector to identify if there are people in the room. Now, how does one do that? You can do that with a camera, but that violates privacy instantaneously. So these guys actually do it with either an infrared sensor or a radar sensor. And it's mounted on the ceiling. As long as your targets are alive and they have their hearts beating, you can actually count the number of people inside of the room. And the use case for AI here is that everything in the world either has a heat signature or has an electromagnetic signature. So you have to be able to tell the difference between a human and, let's say, a coffee cup which is kept on the table and generating heat. This is something that we do with our chips very efficiently inside of that device, and still have continuous coverage of the room where we were able to count the number of people inside and have a battery that basically lasts for 5 years without you having to replace it very often. So this is one of the earliest places where we're seeing AI coming out into the market. And I think as we go into the future, there are more pivotal applications. Think about smartwatches, which are looking at your ECG throughout the day. And 10 years before you actually develop any sort of a cardiac disease, they've detected that aberrant heartbeat, that once in a lifetime sort of beat that occurred, and they're able to tell you that you're at risk of developing some sort of a critical disease, and it flashes a red light on your smartwatch, and then you go and see your doctor. This sort of diagnostics is simply not possible always on today without sending your ECG data consistently to the cloud, and this is something that we've also managed to unblock with our chips.
So for interesting applications that you can finally do right on the edge, first I think across 3 areas, and I'll share a specific one that I've enjoyed. But when you think about kind of new capabilities, right, with this, it's first kind of connectivity challenges, right? Either where you have low bandwidth, like a lot of the LoRa devices here at the show, or intermittent connectivity. AI is hard to run in those scenarios. Now, right, that's possible. Second, I think around privacy, where you have privacy concerns and you want to run that AI locally, right, now that's possible. It's medical devices or things like that. The other is around power consumption. And so, because of the AI models, as have been explained, are more power consuming, you're going to eat up your battery life very quickly. But with the advances in the capability, now you're able to do that more efficiently on the edge. And so one of the more interesting examples that I've seen is around condition monitoring or vibration analysis on machines. So you want to monitor a machine, kind of ultimately predict if it's starting to fail through vibration analysis. So in the industrial industry, this is happening as we speak today. But initially, as they were looking to put AI onto these machines and run them, they would only get maybe at best about 1 year battery life. And they're battery connected because the infrastructure, you're adding these after the fact, and so it's very hard to kind of run power. And so a lot of these devices now, with the advances of the capability, they're actually able to get 5 year battery life, and that has been the goal. And the way that they could only achieve 1 year battery life previously was these systems would wake up once an hour, check, go back to sleep. That's how they got 1 year. But with the improvements, now you can run them continuously, never miss a beat, and get 5 year battery life. So interesting example of finally being able to do that.
So I talked a little bit about the drones where we can deploy our chip and be able to be the interface between the mechanics of the drone and their controller and be able to optimize to depending on the weather and payload and direction, et cetera. So, that's a really good one for our particular chip. The other one Brian talked a little bit about was predictive or preventative maintenance. You know, I worked in a lot of different factories in semiconductor manufacturing. You literally have hundreds of pieces of very, very expensive equipment. And, you know, you're developing these chips or processing these chips, and your downtime is literally measured in the millions of dollars per hour. So when we can deploy our chip looking at a multitude of sensory input, meaning harmonics, vibration, temperature, current draw, the hydraulic pressures, etc., we can look at all that real time and be able to predict exactly when the piece of equipment is going to be able to fail. And then also we can predict it, but we can also go through preventative measures. So if you have, you know, alternate filtration or different ways to be able to intervene, such as different pumping, oil, etc., we could actually modify that and be able to do preventative maintenance before it actually fails. And so with sitting right on the edge, we can sit there and monitor all of these different sensory inputs of the tool, be able to, you know, flag it, be able to prevent it, and then be able to predict anything that needs to happen long term. So, you know, that's exactly a good application of edge AI processing.
Good. No, those are good examples. I mean, one of the interesting things about when you can embed AI on the farthest edge in a battery that lasts, you know, for many years, it becomes like you mentioned, like the peel and stick. I call it the peel and stick deployment, right, where there's no power lines needed. And this actually dovetails nicely with a lot of the low power wireless radio work that's happening here at the show too. So for these, what they call brownfield deployments, right, where things have been in place and they want to add AI sensing to it, you know, peel and stick, and now you manage these devices, you know, and deployments without having to run power cables. It's actually a big deal too in municipalities. We've seen a lot of safety cameras, pedestrian safety, other things that are self-powered, where, you know, you can't afford to, you know, break up the concrete and run power lines and other things. So it all has to be, you know, snap it onto a pole and turn it on and you're done. I wanted to shift in the few minutes we had left. You're all three are from pretty small companies. And we have a lot of small companies here, and probably folks in the audience that are working at small companies or have your own company. So in the AI space, which has a lot of hype in it, do you have any guidance for some of the folks here that are, you know, in these kind of startups in this space? And how have you kind of, you know, your words of wisdom for folks on how to sort of navigate the hype and the reality to build a business in this space?
I'm not sure these are words of wisdom. I think it's just some insights from our own experience, and that's really been that you have to be able to focus on delivering value. When the AI wave actually started somewhere about 10 years ago, and we went out to customers and spoke to them about our brain-inspired chips, it basically seemed like a science experiment. This is what people told us. It felt like. And it wasn't until 5 years later, somewhere around 2020, that the industry really woke up to the problem that AI is going to come with, and that was really power. And that's really when they opened up to innovative new solutions. So the key fact here is that you've got to be able to focus on actual value creation, identify real problems where you can bring these solutions. And for us, we've kept ourselves out of the hype and the buzzwords as much as we could. In fact, we avoided using the word AI for the longest time, because AI also sort of is a very vague term, and you can use that to hide, you know, behind how you actually implement the application. So I think the main message from us is that just focus on value creation, and generally that allows you to build traction very well.
I think for us, we're not an AI company per se, right? We're enabling AI. We're helping that. That's one of our use cases, but we've actually have many other use cases that have nothing to do with AI. So I think for those that are, are looking for funding or looking to raise, I think one of the things that's been important for us is how we map ourselves to AI and not oversell it, but what do we do with AI? How do we help enable it? How do we help improve it? I think it's been important in telling our story, making it more interesting to those that only want to invest in AI type companies, let's say, but see how it's a needed type approach to the market's been, again, important for us.
Yeah, and I agree that at the end of the day, it's all about what problem are you trying to solve, right? It's your value creation or what problem, real world problem you're trying to solve. And so that's kind of why we went and did the drone application to be able to show, hey, here's how AI can extend flight times of a drone, which is really key for people who operate drones in terms of delivery or monitoring borders or whatever the case may be. Getting almost double the flight time or more than double the flight time is actually a very key problem to solve, so that the drone's in the air more. Predictive maintenance, your return on investment on predictive maintenance is huge in a lot of manufacturing facilities. So your rate of return would be instantaneous. And so every time we just use AI as a tool in our arsenal. We don't really try to hype it. We're actually just saying this is the real world problem that we can solve utilizing AI, utilizing low power, utilizing low latency. Those are all key measurables that we use to be able to figure out how to solve real world problems and put those tools to the best use that we have, again, to solve real world problems.
Cool. Okay, so I think we're concluding here. Interestingly, like with the AI hype cycle has gone full swing, where everyone's talking about AI now. It's like you don't want to talk about AI that much. But I really want to thank our guests from Innatera and Atym and EMASS, and please look them up on the web and check out their stuff. And really appreciate your time. Thanks.